Okay, we're going to look at the first two sections of Chapter 6, the new motion topic. It's mainly about the mathematics. It's one of the most mathematical parts of the course. However, today is really the background and the ideas behind it. There are so many different words to describe motion, how things are moving, where they're moving, and we need to also bring in the ideas that why things move, which is descriptions of motion as well. So what we're going to just do is the basics here. Okay, now the first bit is really designed about discussions in the lesson, so we will just nip through that. But in your section 6, if you open up, this is really just for getting your notes, making sure you've got your notes complete. Okay, sun's in and out a bit today, so if it keeps changing colour, the sun must have come out. Okay, so you've done a lot of this already. Okay, I'm sure that some of these things are stuff that you've done back to front, over and over. If you're doing further maths, you'll probably be doing this as well in some of the stuff this year. For everyone else, you will be picking up mechanics at some point. So we are really just going to show you some techniques and descriptions for most of the topic. However, descriptions and what they mean is today's main aim. So there's one thing you can't get away from, and that there's always motion going on to do with Earth's gravitational field. So let me just change that a second. Sorry about that. It seems to be fading in and out with its focus. Right. Okay. So things always fall towards the Earth, and you'll learn at GCSE that varies. That's given a value. When you do this in maths, you will only use 9.81. That is not what we use, so just be really careful. However, the reason they use it is because it's quite general. Okay, when you walk around on the Earth, you will find that the gravity changes. We've known about that for about 2,000, 3,000 years. Arab traders know that if you pick up and buy sapphires, minerals, etc. Near the equator, gold and so on, and then you move further north or further south, then you can trade it for more money because the gravitational field strength further away from the equator is stronger. Things weigh more further away from the equator, and there's different reasons for that: the spin of the Earth, the distance, the radius of the Earth at that point, and so on. However, it gets a bit more complicated because if you do geology, you'll find out that you actually do a lot of work on gravitational fields as part of the measurements. If you're studying physical geography as well, the density of the rock makes a difference as well. So you can measure gravity in different places, on different floors of a building, and you'll get different readings. So we're going to just talk about that in general. We're going to take the perfect value, shall we say. However, how we think of gravity has changed over time as well, and we actually got to something that's been around for quite a while, about 2,000 years, where the ancient Greeks used to measure it. However, Einstein really showed the link of it. So one of our crucial things that we're going to link up to is why things accelerate. Now, you know from GCSE that F equals ma. To make things accelerate, you need a force. Okay, so there's our object, there's our mass, and that's its acceleration. What is the force that makes it accelerate? Well, if you are anywhere in space and we are away from electrostatic effects and so on like that, if it's just down to the factor of gravity, then the thing that's causing the force is its weight. Okay, and from the equations we have at GCSE, we know the weight is mg. Okay, so the mass is acted on by the gravitational field strength. You put them together, you get the weight. That weight is the force that causes an object to accelerate. And so with some fairly simple logic, the mass is causing it to accelerate, but it's also the thing that is accelerating. So effectively, on Earth, we can take the gravitational field strength to equal the acceleration of a falling object. They are in different units, but they actually will be the same if nothing's to complicate it. So I'm going to add a better caveat, that is, it's only true in a vacuum. Okay, so as soon as you get air resistance and things like that, it all changes. Okay, a little bit of background around there. So again, what we're going to take, if you read through, it gives you that initial rate if we have a real object in real atmosphere and so on. However, in the equations, we are going to use 9.81 if there's no resisting forces. There we go. Okay, so that's going to be our go-to thing. Now that isn't in the data book, so as we go through and we go into the forces chapter, the dynamics chapter, we'll get into that habit of labelling them and making sure we're labelling it. So always put mg as an accelerating arrow, a force arrow on a diagram. Okay, what most people struggle with in the general public, and we're just going to make sure we're dead spot on with this, is that mass and weight aren't the same thing. They're two different sides of an equation. One has a multiplying factor, so there's definitely not the same thing. So let's just pick up on these. The mass itself, known as inertial mass, which effectively comes from this idea of inertia, how easy to start something moving or stopping it. Nowadays we tend to call it momentum, so it features in there, but let's just stick with this, how massive something is. Okay, it's a property of all matter, and that's crucial. Matter, mass, momentum, they actually all have the same stem words. Okay, but all matter is massive, it has mass. That is a scientific term, by the way, massive. Okay, so property of all matter, let's put that in to make it obvious, excuse me, they're all massive. Okay, what is it due to? Well, it's due to the fact that it's made of atoms, where they all have relative atomic mass. Okay, so we have that, but also we've obviously got the idea of the fact that some things are physically bigger than others as well. So it's just literally times by n, which is the large number of atoms. Okay, so if we add up all your atoms, they'll each have mass. You get your total mass. It's not genius really, it's how much stuff you are made from. Okay, whereas weight you can have and you can change. Mass you can't, unless you lose some atoms, an arm falls off or something, you're not going to change your mass, but you can change your weight because this is due to both of these factors. Okay, so this is a force experienced by any mass when in a gravitational field. And we'll look at fields in more depth, much more depth next year, but the idea is that, you know, here we have gravity in front of us. There's nothing happening. For you to measure that gravity, for you to experience the gravity, you actually need an object, and that object will then experience the force. Okay, so you can't have the force without the object and the gravitational field. Okay, so never ever ever label gravity as the thing making things happen. It's not right. It's the weight, it's the thing that's producing the force. Okay, just a little caveat as I mentioned at the bottom to round off this first section. The value of G, which is little g, gravitational field strength, I'll just call it G to save a lot of writing, is affected by lots of different things. The shape and structure of the Earth, okay, which I cover in the lesson, because there's a very classic experiment where they actually managed to weigh the Earth. I'll tell you what, let's call it the terrain. So not the Earth itself, but the surroundings near you. If you're down in a hole, it'll be different to not being in a hole or being on a mountain. In which case, also altitude affects it. Not the altitude of the air, but how far you are from the centre of the Earth. And latitude, which is No, it's not. That is definitely 1t, isn't it? Which is not a constant. It is how far you are up the Earth or down the Earth from the equator. Okay, so it's again, it's an angle from the equator. So 9.81 is average for the UK. Okay, and I will make you notice it's 9.81. Okay, whatever. So just going to pick up on a couple of things because it's equivalent but they're not the same. That is in newtons per kilogram. That is meters per second squared. Excuse me, I've done a slash there and haven't there. So newtons for every kilogram, whereas that's how fast something is changing its velocity. Okay, but the values are the same because they are equivalent. They are not the same, they are equivalent. How big they are, their magnitude is the same. Okay, so again, just to kind of really clear that up a little bit. Okay, we'll jump straight into the second section because this is one of the biggest things, and I know you spent quite a lot of time on this at GCSE, so we'll kind of make sure we don't rehash this. So what we've got, things are how they move and where they move and how fast they're moving, all can be summed up in certain terminology. Okay, so differences, we can talk about the distance something's travelled, we can talk about displacement. One is not any more scientific than the other. Sometimes it is more correct to talk about distance than it is displacement. Okay, fairly obvious example I think is this. So if we're to travel from you know, your classic A to B, if you go via the long route, that's the distance you've actually travelled. How far you are away as the crow flies, so in a straight line from your starting place, you haven't gone very far. Okay? And the more circular or more circuitous route, the further you'll go, but actually you might not end up very far away. And if you have something like a track, well, this is you on your journey to work, this is home, this is work, via a different route, you get back, you always end up at home, so effectively you haven't gone anywhere. Okay, so this is what we mean by displacement. Distance is how far you have actually moved. Okay, so they're slightly different. One is obviously a little bit more complicated than the other, which leads us into where it goes, which is speed versus velocity. Okay, so this is probably where you picked it up the most, but we will come back to the fact that we're going to be looking at more complicated motion at the end of the year into next year. Okay, so how things move in a complicated way, we need to actually use both phrases, displacement and distance, quite a lot. Okay, and interchangeably. So speed is simply the distance. Okay, so it's the distance moved per unit time. Okay, so if we were to define that, it's how far you've gone per second, per hour, per minute. Okay, the crucial thing is it is scalar, which is simply, again, before people go, well, that's not really important, it is. The scalar stuff is really good. If we can use scalars, it means that if the direction is not important, okay, then we don't need to you know, think about distance and direction at the same time. So it's effectively, it's just increases or decreases. We don't have to worry about any other complication. Okay, and this is particularly true for the description itself when we're thinking about that idea of motion. So very useful for, I'll put this brackets, e.g. circles. Okay, so we will talk about the speed quite a lot. We might also talk about velocity at the same time, and they can be slightly different. Okay, so definitions wise, it's a measure of the displacement Okay, so it links the two together, and if you go back to the previous page, excuse me, writing and talking at the same time, displacement moved per second. Now that's a bit of a rubbish way of putting it. Okay, again, per unit time. It's far better to talk about the rate of change of displacement. Okay, or rate of displacement change if you prefer. What that means is it's actually at every single moment in time. Okay, so sometimes we call this the instantaneous velocity. At any instant. Okay, so that's what we mean when we're talking about the velocity. So often you'll see in some videos or sheets or so on, not so much from what we do, but instantaneous velocity is just the velocity at that moment. So the correct way of writing it, okay, to bring it in, is to think about everything and how it changes. So it is a vector. Okay, so that's really important because I'm going to give you two versions here, which links us into this one. Its definition, I'll give you the equation V equals ds. We'll come back to that later in the chapter, but S is displacement. Bit of an odd one to use, but dt. Now that some of you may be starting to experience about now in further maths. This is what's known as differentiation. Okay, and it's a method of finding points on a graph where the graph is changing. So this is not to do with finding how the distance has changed each second, because in the second it might be changing speed, speeding up, slowing down, etc. So it's at these d's, the ds by dt, signifies at an instant. Okay, so at a single incident, okay. Or let's just change that. Instant probably makes it clearer. We won't get mixed up with light then, will we? Okay. Whereas, okay, average velocity is slightly different and really kind of links the two together, so they both come into this. Okay, and the average velocity still is a vector, so put that in. Oops, excuse me. But it's relating to several things at the same time. Okay, and really it's a bit of a rougher way of doing it. So what we're going to say with this is that this, I'll give the equation to start with. V, again I've put a little tick to show it's a small v for my writing, equals delta S over delta T. Okay, and that means change in displacement. Okay, now let's add a bit more. It's not just the displacement at that moment or where it's going around, but change in displacement overall. So if I was to drive a long way, my average velocity won't be what I see on my speedometer, my instantaneous velocity will. You know, if it takes me 5 hours to get to Glasgow, that's around about 50 miles an hour. Some moments I'll be going faster, some moments I'll be going slower, and that's where the average comes in. So there's a change in displacement overall over time taken. Now, a really useful thing to think about this is that if we're talking about average velocities, it's really nice to put on a graph. So we're going to go into graphs in our next section, but simple idea is it's the average of the starting and the final velocity. Yeah, so it's also worth pointing that out. So V, and I'll just put average as a little subscript on both those. So V average is initial plus final velocity. So we've got two different values. You simply add them up and because you've got 2, divide by 2. Okay, so it's a really nice, nice useful thing to think about. So we will see these in different ways, but the far easiest way of thinking about them is when we put them on a graph, and it really sticks out. One of them is about the gradient, one's about the average gradient, and this one is ignoring whether the gradient's going up or down. Okay, so depending how we use the language, each one can tell us a lot more than the other. So it's different ways of using things in whichever is the most useful. Okay, acceleration, that seems to have slipped, that should be over here. Using a similar idea to instantaneous velocity, the acceleration at any moment is also the rate of change. So it's not how much it's changed, unless we're being very average about it. So if we're thinking about it, we want to use it in terms of what's going on. Now, just to be precise, this is how we also describe motion. So if you're talking about the motion of something, you've been asked to describe it, you need to mention velocity, you also need to mention acceleration. Okay, they're both important. Why? Because if the velocity is changing, then you have acceleration. Okay, so you combine them into the same sentences. So, crucially, bum, 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 bum. Okay, following on, because we are integrating this, so this is gradient. Gradient can be positive or negative, i.e. it matters about direction, it's a vector. It also means that the acceleration can be positive and negative. Okay, and this is a little bit hard to get your head around, so at the moment I'm just going to put the notes in. When you watch the videos, when we're talking lesson, I'll try and demonstrate it in a way. Okay, but if you imagine our thing was moving, I'll just grab my little car out of here a second. There we go. If my car is moving forwards and it's getting faster, then it's accelerating. If it's moving forwards fast but it's slowing down to a halt, then it's also accelerating. It's just that it's getting slower rather than faster. Okay, so we're not going to use the words acceleration and deceleration, if at all possible, in our descriptions, because it can get confusing. I'm going to show you that now. What we'll just talk about is positive or negative acceleration. So, move Bob out of the way. If an object has a positive velocity, now what does that mean? I'm going to come out with the fact that we tend to use Cartesian coordinates, i.e. moving right. Okay, so we tend to take that direction, like on a graph, we're going to take that direction as positive, that direction as negative. Okay, we'll come back to vertical and sideways another time. If it has positive velocity and acceleration is positive, then what that means is your speed is going to increase. Okay, then velocity increases. Okay, so that means if you are moving right and you are being pushed, forces making you accelerate. If the force is making you accelerate to the right, then you're going to get faster as you go to the right. Okay, but if you have negative acceleration, okay, so that means, I'm going to add some arrows in here, so acceleration I'm going to add as a double arrow, so that's my acceleration. Okay, so if I've got velocity going that way, single arrow, double arrow for my acceleration, then what I end up with is that gets faster. If I've got negative acceleration, then, sorry, on an object that's going to the right, then my direction of force, my direction making the acceleration change the speed of the moving object, is going to the left. So it's going, crash. If the car goes that way, the force is against it and it slows it down. okay, then object decelerates, okay. I'm not going to put that because I think you need to keep coming back to velocity all the time. Decreases velocity. Okay. So keep on thinking of acceleration in terms of change of velocity. So that's got your velocity that way again. Okay, but your acceleration is that way. Okay. If we're swapping it around, in other words, it's moving with negative velocity, it's moving to the left, so moving left. Okay, as I say, we always take that positive to the right, keep it simple. Some people try and swap it around, but it just gets confusing. Keep it simple, just like a graph. You're so used to those. So if we have that one, then basically positive acceleration, okay, means that they're accelerating that way, but it's moving that way, so it's going against it. So actually that decreases velocity. And if we have negative acceleration, then what's going to happen is, because the acceleration is to the left and it's moving to the left, it's going to get faster as it goes to the left. So that increases velocity. Okay, so it can get a bit confusing, and that's why it's easier to keep with a direction that makes sense. So you just think, is the thing that's making it accelerate, usually easier to think about forces, if the force making it accelerate is in the positive direction, pushing that way, what's it doing to my vehicle? Is it moving it sideways? Is it moving it faster? Is it moving it slower? Okay, so to sum all that up, probably the easiest way is to think of acceleration in same direction as velocity increases the speed. I'm going to put speed there on purpose. Okay, so it's not going to change direction, it just makes it go faster. Keep it simple. Obviously, if it is opposite of that, then it does the opposite of that. Okay, so if it's in the same direction, velocity, acceleration, crucial little phrase there, I think. Now, just to bring that all together, okay, we obviously need an equation to go with that. Well, it's all about that change in velocity. I'm going to go with average at the moment, then we can get onto the more complicated stuff. So I'm going to go with, be precise, average acceleration is change in velocity per unit time. So very similar to the displacement being over time taken as well, so per unit time. What that means is, for what we're going to do, I'm going to just talk about delta V over delta T. Okay, which is not great. We will become more scientific with it, but that will do. Change in velocity. How much has velocity got, faster or slower, and how long did it take? That's what gives you your average. And you may want that in a better way. I know you've used some letters, but we'll keep off those at the moment when we explain them. So, excuse me. He says probably doing the letters. So velocity 2 subtract velocity 1. So take your starting value off your original value, you get your change in velocity. Okay, that is important, doing it that way round, otherwise you end up with all the wrong signs on your numbers. Okay, again in the lesson we spend time on this, but just in terms of notes, what we're talking about when we're talking about acceleration is how much that velocity changes every whatever unit it is, and it tends to usually be seconds. Even if it's not in meters, that will be in seconds. So here we have something that's moving with a speed of 15 meters per second. Okay, we're ignoring direction, so it's just moving at that speed. If the acceleration is both positive they're all positive, there's no negative in there, there's nothing to say anything else, then what happens is we're getting faster by 2 meters per second. So every second we've got 2 meters per second changing, and we'll just keep going up like that. So another 2, another 2, another 2, another 2. Okay, so what you can imagine this on a graph, it does depend on what type of graph, but your change is nice and steady because your acceleration is steady. Okay, now that's what we call uniform acceleration, steady acceleration. It doesn't need to be. That appears to have slipped off my page, so I will correct it before I send it out to you. Here is our non-uniform. So we've got different accelerations. It looks like someone's pushing their accelerator, if that's what it is, more and more and more. Okay, so they're not just holding their accelerator for constant acceleration, they're actually changing it. And so if in this case we're starting from 0, again we just after 1 second have increased the speed by 2. Then our speed has increased in that next second by 4. Okay, so we're actually just getting bigger, then by 6, then by 8, okay, etc, etc. So when you put that on, 42 and another 14, that makes 56. This will not give you a graph anything like the one you've just imagined. I'm guessing you imagined a straight line graph. It can vary, it can change. This acceleration could go up and go down. Okay, it will still get faster as long as you have acceleration. Okay, so go back to the initial idea. Acceleration is a change in velocity. Okay, more specifically, it's the rate of change of velocity, but there we go.